Hello everyone, I welcome you all for the session of Sliding Contact Bearings Part 2. The objectives of today's session is to understand McKee's investigation, to study Petroff equation for identifying the change of parameters in bearing. Now, in my previous video, we have discussed about the basic of bearing, its classification and the different modes of lubrication. So there are three modes of lubrication. One is zero film lubrication, another is thick film lubrication, and the third one is thin film lubrication. So here are the diagrams of thin and thick film lubrication. So in talking about thick film lubrication, initially when the shaft is at rest, so here in the diagram A you can see when the shaft is at rest, so it is in the contact with the bush. So journal is in contact with the bush. Journal is nothing but the shaft. As the journals start rotating, so initially it takes some sufficient time to build up a pressure in between this clearance space. So, and also you can say there is a thin layer of the fluid in between these two initially. So you can say there is a partial metal to metal contact in this region. So it is nothing but the condition of thin film lubrication in which there is a partial metal to metal contact. Here in the region A you can see it they are in contact, two surfaces are in contact, whereas in case of B region you can see there is a fluid in between these two, or there is a lubricant in between these two. So you can say in the initial condition or in the starting condition, or when the speed of the journal is very low, in that case there is a partial contact between the two surfaces, or there is a metal to metal contact, partial metal to metal contact. Whereas as the speed of the shaft goes on increasing, it forces the fluid to pass continuously into the oil wedge or in the wedge shape clearance space. So in that case a sufficient amount of pressure is built up to oppose this force. So in that case there is no contact between the journal and the bearing. So you can say that while discussing about McKee's investigation, this is the diagram, and you can say that there is a transition of thin film lubrication to thick film lubrication as the speed increases. So in case of hydrodynamic lubrication, initially there is a thin film, and as the speed of the journal goes on increasing, it passes to the thick film lubrication. So now this statement can be more discussed or elaborated by this diagram, which is mu n by p curve. It is called as mu n by p curve. This curve is given by Max brother. Two brothers are there who have investigated on this thick film and thin film lubrication in hydrodynamic condition. Now on the x-axis there is bearing characteristic number. It is nothing but the dimensionless parameters, group of parameters. It is nothing but the dimensionless group of parameters. And y-axis consists of coefficient of friction. It is given by tangential frictional force to the radial load acting on the bearing. Okay. Now in the diagram you can see, so this is the bearing characteristic number mu n by p, where mu is absolute viscosity, n is the speed of journal or shaft, and p is the unit bearing pressure. Now here there are two regions, one region and this is another region. Now in this region there is a thin film lubrication, whereas in this region there is a thick film lubrication. So you can say this BC curves shows you thin film and CD curve shows the thick film lubrication. Now in case of thin film lubrication, there is partial metal to metal contact, hence there is more friction. So here you can see coefficient of friction is more in this case, and as it moves in the forward direction it decreases. Now here again you can say in case of thick film lubrication, frictional losses are less, comparatively less. There is no metal to metal contact directly, so this curve goes in this direction. So here the parameter which affect is viscosity, and here the parameters which affect is surface roughness and chemical composition of the lubricant. Now, value of bearing characteristic number at minimum coefficient of friction is called as bearing modulus. It is denoted by K. Bearing modulus is nothing but bearing characteristic number at minimum coefficient of friction. So you can say it is at point C. Bearing characteristic number at point C, and it is given by K. Now, actually, working near this point C should be always avoided, or working at this bearing characteristic number should always be avoided. Why? Because if there is a slight decrease in speed or slight increase in load acting on a bearing, this will lead to bearing to pass into the thin film lubrication, or you can say in boundary lubrication. It will result in boundary lubrication. It will increase the friction and it will lead to the wear of the bearing surfaces. So bearing should be operated in this region. So working nearby C point should be avoided. So this is your critical condition. Now to avoid this, says here, operating value of bearing characteristic number, it should be at least 5K to 6K, that is 5 to 6 times of bearing modulus. And if the bearing is dealing with fluctuating loads or impact conditions or impact loads, then in that case the bearing characteristic number should be 15 times of K, that is bearing modulus. The significance of this curve is to understand the stability of hydrodynamic bearing, hydrodynamic journal bearing. So these curves give you the region in which the bearing should be operated under stable condition, because thick film is the stable and thin film is the unstable, as there is more metal to metal contact and more friction and more wear. Now next we'll discuss about Petroff's equation. Now this equation is used to determine the coefficient of friction in journal bearing. Here is a correction, it is journal bearing. The assumptions is, first is shaft is concentric with the bearing. Second is bearing subjected to light load. Now practically these conditions are not possible, because shaft is always eccentric with the bearing and bearing is always subjected to high load. It is not possible to work on light load. But now in this case there is a need to study Petroff's equation, because it gives a group of dimensionless parameters which governs which defines the frictional properties of bearing. It defines the frictional properties of bearing. So by using this equation we can easily find out the properties of the bearing. So we have to study this. Now this is the diagram showing the journal and the bearing. This is the shaft, and the shaft which is inside the bearing is called as journal, as we have discussed. This is the clearance space which is denoted by C, that is clearance. R is the radius of journal. Ns is the speed of journal. L is the length of bearing. This is the first diagram, and in the second diagram also there is one load acting on it. What is that we will see later. First we will discuss about diagram number A. So in this diagram now, so this is the journal. Velocity at the surface of journal is given by mu is equals to 2 pi r into ns. Now 2 pi r is nothing but the circumference of the journal into speed of the journal. Next is according to Newton's law of viscosity. According to Newton's law of viscosity, I hope you all are knowing about this. So the formula is P is equals to mu into A in bracket U upon H, where P is here nothing but tangential frictional force. A is the area of journal surface. A is the area of this journal surface. Now this area is nothing but circumference into the length. Length of the bearing is equals to the length of journal. So you can say circumference into L. Now this is the condition, these are the conditions when we are applying the viscosity rule, Newton's law of viscosity in this region. So area is given by 2 pi r into L, area of journal surface. Now next is we know that U is nothing but the velocity at the journal surface, and H is given by distance between the journal and the bearing surface. Distance between the journal and the bearing surface. This is journal surface and this is bearing surface. It is nothing but equals to clearance. So now substituting these values in equation number 2. So equation number 2 is mu A in bracket U upon H. Mu as it is, substitute A, substitute value of U, this value 2 pi r into ns, and H as C. So your equation becomes now 4 22 pi square r square into L into mu into ns upon C. This equation upon C. So this is nothing but the tangential frictional force. Now frictional torque. Frictional torque can be given by frictional force into radius. So frictional torque, mt is nothing but torque, and frictional torque, so mt suffix f is equals to p into r. Now p, this is the equation, this equation into r, so r square become r cube. So this is nothing but your equation number 3, which gives you the frictional torque acting on a bearing. Now next, here is the second diagram, in which consider this W as a, now this W is nothing but radial force acting on a bearing. So unit bearing pressure, it is denoted by small p. Unit bearing pressure acting on the bearing is given by W, that is radial load upon projected area of bearing. Projected area of bearing. So P is equals to W upon projected area of bearing. Projected area of bearing can be written as twice R and L, twice RL. Twice R is nothing but diameter into, this twice R is diameter into L, length of journal or length of bearing. So you can write over here W is equals to 2PRL. This equation can be written as W is equals to twice of PRL. Now next, frictional force. Now frictional force can be written as in terms of W, F into W. Frictional force is given by F into W. So frictional torque, it is given by frictional force into radius. So frictional torque is Fw into R. Now this again we can say that frictional torque, it is nothing but mt suffix F, it is equals to this equation. So substitute the value of W, 2PRL. 2PRL. Here we have substituted the equation of W. So this is equals to, this gives you F into 2PR square. We are multiplying over here it by R. So this becomes R square into L. So this is equation number 4. And again we are having this equation number 3. It is also for mt F, that is frictional torque. So we are having two equations for frictional torque. They are given by equation number 3 and 4. So equating equation 3 and 4, you will get this equals to this equation. So this 2 get cancel out. Here it remains 2. R square cancel out. So here simply remains R. L get cancel out. And rest of the term remain as it is. So you can write the equation in terms of F. F is nothing but coefficient of friction. So you can write the equation in terms of coefficient of friction. As we are saying, Petroff's equation is used to find out coefficient of friction. So it is equals to 2 pi square into R upon C, again in bracket, mu ns upon P. So by rearranging these terms, you will get this one term, second term and third term. Now here R by C and this mu ns by P is nothing but or you can say this Petroff's equation gives you the dimensionless parameters. These are the dimensionless parameters that governs coefficient of friction and the various properties like frictional torque. So once you are getting this, you can find out frictional torque, frictional power loss and the temperature rise in the bearing. So Petroff's equation is used to find out to study the different properties, frictional properties of the bearing. So with this, we will stop over here. Thank you. If you are having any doubts, kindly write in comment box. And if you understood it, then kindly like, share and subscribe. Thank you.